So this is our final year project. It is called CommentARio. And if you remember what we've done in the last semester, well, we have a comment system that allows people to leave their comments on the real-life object. And in the last semester, we use Euphoria SDK to realize our thinking. In this semester, we totally get rid of Euphoria SDK and we build the augmented reality backbone with our own system. And why we want to build this common system, it is because we find that the comments on a certain product is very variable to both the customers and the producers. For producers, he can use the user comments to adjust their selling strategies, and for customers, he or she can think twice before buying this product. And also, the Euphoria Cloud Recognition is kind of close and it is not suitable for research experiments. So in this semester, we study how the flat target recognition can be performed, and we later extend it to use it to recognize the target beyond those flat targets. For example, we make out a method to recognize the cylinder target on the cloud. And in this semester, we build a target recognition pipeline and a server and an app that can demonstrate the cloud recognition. And also, we work out a method to recognize the cylinder targets. This is designed for recognition of the soda cans. And we mainly use 3 SDK or theory in our development. The first one is OpenCV. It is a popular computer vision library, and the feature detection algorithm we use is called SURF, known as Speed Up Robust Feature. And we also reuse our common infrastructure built in the last semester.
So our objective is that firstly we need to implement the recognition without using Euphoria. Can we build our own cloud recognition server? We build our app that recognize the targets and still display the comments like bullet, like our last term's app. And we try to support other types of targets like beyond the flat target, for example, cylinder target.
And as you can see here, this is the target recognition pipeline we work out this semester. And for the feature detection, extraction, and matching part, it will be the same when you are using other feature detector, for example, SIFT and ORB. So our main contribution is at the image enhancement and find homograph and homograph test part. And now we will briefly introduce the method of image enhancement.
So SUF as a sophisticated scheme actually has some robust design, but as our experience shows that it's still sensitive to noises in images. If the image taken is noisy, it would have many false key points and it would hinder the further recognition. So we perform 2 kinds of enhancements. Firstly, we perform bilateral filtering. This is basically smoothing, but it somehow preserves the edges of image, so the recognition would be still feasible. And the second one is some common histogram equalization.
And as for the matching part, we use speed up robust feature detector, and also the extractor. And for the SURF, it is scale invariant and location invariant and angle invariant, and so it can be used to detect the target on the scene. And as for the matching part, we find that the matching part is the most time-consuming part. And for our cloud database, we use a small size image database. So we find that brute force feature matching is the most efficient one with our database.
Okay, then comes to the result selection. So the matches that actually matches the key points in the scene to the key points in all the target candidates. So in this step, you still don't know which candidates gives the best match. So we propose an approach to determine the best match and test whether the best match is good enough and is unlikely to be a false positive. Firstly, we find the mean distance in all the matches, and we pick up good matches that is close, whose distance is close to the mean distance. In this way, we firstly filter out good matches for all the candidates. Secondly, we vote for the best matching candidate, which means we select the best matching candidate as the target with most number of good matches. This is our best matching candidates. Thirdly, we'll perform a homography test. This is actually some multi-step involved. So the step one is that we use the matched key points to find the homography transform. And the second step is that we use the homography transform to transform the corner in the original image to the corner in the scene. And the third step is that we use the corner in the scene to check the it would construct a contour from the corners in the scene, and we check whether the contour is good or not. So the criteria is that we find the mean bounding rect around the contour and see whether the contour can enclose a significant portion of the area inside the bounding rect. And if the portion is significant, we accept the target because our target is all rectangle, so it would likely be still rectangular-like in the scene. But if the contour is very messy, we think that this is not a match and it's likely to be false positive.
So here comes the method of cylinder target recognition, and it can actually infer from the flat target recognition instead, because if we carefully observe a cylinder, you can see that the central part of the cylinder image remains relatively undistorted, so it can behave like a flat image. So the method we use to recognize a cylinder target is to divide the lateral image of a cylinder into n segments with p% overlap area. And the best segmentation, according to our experience, is to divide a lateral image into 3 parts and with 50% overlap.
So then comes the implementation. Our implementation is based on some library, but it's not very high-level libraries like Wolfovia. We use something like OpenCV to get some building blocks from the computer vision theory, or we use Android SDK Codeva to build the app. So which is pretty standard. So for the recognition server, we use Linux API, C++11, and OpenCV. We find that C++11 is a pretty good choice because it still has the performance of C++, but without much annoyance in early version of C++. And the web API is built on Flask and run in Apache with more WSGI enabled. And our Android app is built using standard Android SDK with a little amount of whatever. And we also propose some scalability schemes, like we use tree-like matching, such as FLLA, and to instead of brute force to allow matching a very large number of targets. Or we use a worker merger model in a cluster so that we can have multiple workers searching for the target simultaneously. And we can get the result faster, but for some reason we do not have the resource to test these ideas. So it would be our future direction. Okay,
So as you can see here, these are the results of our algorithm, and this is the key point extracted from a target image, and this is a scene image, and we use the scene image to query the image database to find out the best match. And for the yellow box here, as you can see, is the homography, rectangle homograph of the image here, and the red spots are the good matches. And this is the user interface of our Android application, and this image shows that a cylinder target is successfully recognized, and it can also recognize this. The cylinder can also be recognized from another angle, and we map those segment of images into the same product ID so that only one target is recognized from when it is viewed from different angle. And this one is an example of the recognition of user uploaded target, because you won't be able to find the perfect cover image of this book. This book is published by the Chinese University of Hong Kong, so it is user uploaded target.
Okay, so our conclusion is that our recognition accuracy is on par with Wuforia because we test with the Wuforia provided samples, and our system works well on these samples. And our cylinder recognition method is feasible, so as shown before. And we believe that our system is suitable for research experiments because all the stuff are actually open, so you can tweak whatever you want. Unlike Wuforia, you are pretty restricted in their model. Okay.
So for the future direction, as we said before, we can implement the scalability schemes on the server, and we can another direction is we can implement the first 3-step of the target recognition pipeline at the client side, and put the most time consuming and also computing consuming part, the matching part, on the server, and put the remaining part on the client side so that the client side can track the objects. So that's all for our poster presentation.